Hey, chemistry fans, we are back to kind of wrap up the learning part of the gas unit. And then again, a reminder, this will not be on this week's exam. We'll go into next quarter with gas law stuff so we can do some virtual labs. Anyhow, of course, the last thing we need to cover is stoichiometry because that's a part of everything. And really, as we've looked before, since we started stoichiometry, the key here is just how do you get to moles? So if you think about it, we looked at stoichiometry using mass and molar mass, and that was moles per gram, moles, dividing grams by the molar mass. And we also did it with solutions with concentration, which turned out to be the molarity times a liter. Okay. Now, we can use it for gas reactions, and as you're going to see, it really revolves around using the ideal gas and solving for N. So, but let's do a big overview. Way back when we first started stoichiometry, I had the grams of the stuff I knew, X. I can turn that into moles, X, by dividing by the molar mass. And then I can figure out the moles of the stuff I want, because then I can multiply by my mole ratio and get my moles Y. And then, of course, multiplying by the molar mass of substance Y gives me the grams of Y. So that's what we did early on in our first thing in stoichiometry. And then this only changed with solutions, because then to go from grams to moles, we just multiplied the molarity times the liters. What comes in now is the ideal gas law. Okay. And so how I get to those moles is if I know the pressure, the volume, and the temperature, and of course I always know the ideal gas constant, then I can always find the moles. So I can find the moles of X with the ideal gas law, use the mole ratio, and then find the moles of Y and whatever I might need to. And you're going to see a few examples. Oftentimes on this side, I can look for grams, but oftentimes I'm looking for volume. What's the volume of that gas? How much space is it going to occupy? That might be a more important question. Anyhow, this is best done by going through examples, so let me show you a few. Here's our first sample. Methane burns in oxygen, combustion reaction, producing carbon dioxide and water. And so you have methane gas in a 1.22 liter container. It's at 15 degrees, and it has a pressure of 328 kilopascals. Okay. Our first question, and we're going to use this equation and stuff for a while, is our first question is what volume of oxygen would react with all the methane in that combustion reaction? And of course, your balanced reaction. So here's what we know. We know methane's a gas, and we know the values of it, the volume, the temperature, and the pressure. We can use then the ideal gas equation to find the moles, and we've got our mole ratio here because this is what we're looking for, but we're looking for the volume of it. So when we solve this and find the moles, we use that to find the moles over here, and then we can plug it into the ideal gas equation to find the volume. Okay, so there's the ideal gas equation. Here's the values for methane. And with pressure and temperature, oftentimes we assume that they're in the same container, and so they're under the same pressure, same temperature. Sometimes they're, the gases pass into a different container, so that can be changed. But right now, we're just going to assume that they're under the same pressure, temperature in the container. Okay. So the first issue then is, and I've just rearranged this so that as we're looking for moles then is pressure over volume. If I rearrange the algebra, then it becomes PV over RT equals N. So here's our pressure of methane. Here's our volume of methane. 8.314, excuse me, is always the R constant used with kilopascals. And I took my 15 degrees, add 273, and got it into Kelvin. That then tells me my moles of methane is 0.167. Now, knowing stoichiometry and my balanced equation, I can find the moles of oxygen. Okay, so that's my 0.167, and the mole ratio is 2 to 1. So you see the moles of methane cancels. I'm left in moles of oxygen. It's just twice that number, 0.334. Now that I have my moles of oxygen back into the ideal gas equation, I can go and I can find the volume. And again, my value of pressure is still the same. They're in the same container. My moles now have changed. My temperature is still the same. Now, when I rearrange the algebra for V, it's going to be nRT over P, and I can then use that to solve. So my moles now was 0.334 for the oxygen. R is always 8.314 with the kilopascals. 288 Kelvin was my temperature. 328 was the pressure that the oxygen was under. And I solve and I find that's about double the amount of liters, which makes sense. If I doubled the moles, I should probably double the volume if they have the same pressure and temperature. Okay? So that's one way to do that. Now, using the same equation, let's ask another couple of questions. How about, okay, and I've got the equation there, how many grams of water are produced? Okay. Well, I've already done the work to know that I have 0.167 moles of methane. That we did in our previous portion of this problem. Now, it's just now, again, I've got my mole ratio, 2 to 1, so that gets me into moles of water. And then as we know with stoichiometry, if I want grams, I just multiply again by the molar mass. And I end up with about 6 grams of water produced in that same reaction. Okay. Or the final question I could use, what if the carbon dioxide then bled off into a different container, which was at standard temperature and pressure? And now it's saying at this point, if only 2.15 grams of the total of the amount of methane was actually burned, how much carbon dioxide at STP? So it is very possible to have this, and this is really more realistic. I have this reaction going in one container. And what's happening is the water vapor and the carbon dioxide are, because of density, filtering off through a tube into another container. And it's very possible that I have these containers at a different pressure and temperature. Okay. So again, I know I can get my moles of carbon dioxide because I know initially how many grams of methane I had. I can just multiply by the molar mass and get my moles. And extending my dimensional analysis, then it's a 1-to-1 ratio. And so whatever the moles of methane were also the same moles of carbon dioxide. Now that I have the moles here for carbon dioxide, now I can look at my standard temperature and pressure and go into the same and plug it into the ideal gas equation. So there's my ideal gas equation. There's my values, 101.3 kdWb. My moles I just found out, the temperature. These are both standard temperature values as we've talked about before. And now I plug into the ideal gas and solve for the volume. So again, it's going to be, if I rearrange this, its volume is nRT over P. I plug in all my values. There's my moles, there's my constant that goes with kilopascals, there's my temperature, and there's my initial pressure. And I turn out it's about 3 liters that would occupy. So there's a few different ways just with one problem to solve, to use the ideal gas equation and stoichiometry together. Okay, let's look at a couple more samples. Here's another one. How much ammonia gas can be made? Or ammonia gas is synthesized from nitrogen and hydrogen. Okay, we've seen this reaction before. You'll see it when I put it out. What volume of ammonia at 4.5 atmospheres and 80 degrees centigrade can be obtained if you use 7,500 grams of hydrogen? So here's one where you just know the mass of the stuff you have. And the stoichiometry is really no different. You're going to turn that mass into moles. You're going to do a mole ratio, and you're going to plug it into the ideal gas equation. So let's look at that. First, you need a balanced equation. There it is. Okay. Now we know the grams of hydrogen. We're 7,500 grams. So the first thing we got to do is, in finding the moles of ammonia, we got to take the grams of hydrogen, okay, divide by the molar mass. See, hydrogen is diatomic. That's going to get us moles of hydrogen. Then we're going to multiply by the mole ratio. In this case, it's 2/3. Okay, the one you want over the one you got. And that's going to get me into moles of ammonia. Okay, and it's about 2475, half the number. Okay. Now I can use that moles to go now into the ideal gas equation with the pressure and temperature that I was given ammonia under. Okay. Oops, sorry for the typo. That should say 4.5 atmospheres. And I have my moles, and I have my temperature, 80 degrees plus 273. Again, sorry, this should say 4.50 ATMs. Somebody can't type well and match up as units. Okay, which I did correctly here. So I don't know where my mind was at there, but I apologize. That should say 4.50 ATM. So again, to find the volume, okay, it's going to be nRT over P. So here's my moles I just figured out. 0.0821 is what we use for the gas constant with atmospheres. Here's my temperature, 80 plus 273 to get it into Kelvin. And there's my 4.5 atmospheres. Plug and chug the math, and it's just under 16,000 liters. Okay. So that's another method. You're given the grams, and you just have to use the ideal gas at the end. One last moment. Hydrogen and sodium hydroxide is produced when sodium metal is added to water. It's a very violent, bubbly reaction. What mass of sodium is needed to produce 20 liters of hydrogen at standard temperature and pressure? Now here's one where you use the ideal gas equation first, find the moles, and then you're doing kind of a regular stoichiometry problem. Okay, so we'll walk through this. Need our balanced equation. So you mix a sodium metal. It's just a soft little metal stored in oil, very reactive. You throw it in a little bit of water. It just buzzes around with a lot of energy and bubbles and releases a lot of hydrogen gas. You end up with a little sodium hydroxide solution in the end. It's very possible, as violent as it is, when you throw the sodium in, it actually forms a ball. And it can trap stuff in there so that if it's reactive enough, it actually has a little explosion to it and a little flame coming off. Anyhow, the first thing we need is our ideal gas equation, because we need to know the moles of hydrogen gas that were produced. Okay. Now it's at standard temperature and pressure. I use 1 atmosphere and 273 as standard temperature and stuff. And it told you you had 20 liters. So you're going to plug this in here and find the moles. Okay. And again, when I rearrange for moles, it's the pressure and the volume over R and T. Everything's plugged in. My moles is 0.892. So that's how many moles of gas there were. Now I can do my stoichiometry, take my moles, I can find my grams, because now I take my moles, I multiply by the mole ratio, and then of course to go to grams, you just multiply back by the molar mass. And if I do all that, I need about 41 grams. So then I could go get 41 grams, throw it in an appropriate amount of water, produce that much gas. Okay. So that's really how stoichiometry and gas laws work, I'm going to have a short little homework quiz. Again, one of those that doesn't directly count for points other than as I add up and look at the homework you're doing while we're on distance learning. And then on Wednesday, as we kind of prepare for stuff later, I'll also have a few problems for you on a worksheet to work through on your own and a little more practice. Anyhow, that'll do it for today. We're starting week 2. Make sure you continue to communicate and drop into office hours if it's getting very frustrating. I know from surveying folks that most of the issue last week was just the technology piece. And there's a lot of people at school that can help us with that, and there's a lot of things I can do to help you relieve the stress. So don't forget to reach out. Anyhow, that'll do it for today. Have a great day, chemistry folks. Stay safe, stay apart, stay healthy.